Hello, I'm Yegor Prikazuk, and this is the user guide of SCOPE, Soil Canopy Observation of Photochemistry and Energy Fluxes model. Today, we are going to talk about BRDF simulation, bidirectional reflectance distribution function. What I expect you have already done is you went to our GitHub and you downloaded the model with download zip. After that, you have unzipped the file, and now you can navigate to Scope Master, and you see these files. Also, of course, you have MATLAB, which would normally start with double click of Scope. See that the Scope is open, and we run it for the first time. The first run has 100 simulations, and hopefully you get the same message that the output is the same as in the verification dataset, which means we are good to go. What I also expect you to do is to find our documentation. The link is directly in the README. In the documentation, you can see a little bit of description of what BRDF is under Model Capabilities BRDF, and I will give you also some background now. What we are going to do is we are going to run Scope in order to be able to plot these polar plots, and also we will understand what those plots mean. Now, we can go to the main directory of Scope and change input. In input, we change, as always, these three files. First, set options. We are going to say that we don't want to verify anymore. The simulation is 0, so single runs, individual runs, and we are calculating directional. So line 12, we set 1. We save it, we close it. Input data default stays the same for now. File names, we are going to change the second column in simulation name, just to call it directional. But this is purely for aesthetics. So we save it, we close it. Very importantly is to go backwards and to go to set parameter file names and specify here that we are using those three files and not input data like the hypercube, but input data default. Now again, save it, close it, and run it. You will notice that takes more time than usual. We see, in this case, 8 seconds on my system instead of 0.3 seconds. That's because Scope ran iteratively over many angles in order to be able to reproduce the structure. Let's go first in the output folder, which is output directional. And we see here there is a new folder called directional. If we go, for example, to our verification run, we see the directional folder was not produced. That's because we changed option simulation to directional. Inside, there are files, text files, with angles, fluorescence, reflectance, one reflectance factor, and thermal emitted radiance. I would like to plot it, and for that I go to plotting functions, and I go to plot directional. If you stay in workspace, then you could use this command as well. So as soon as I plot it, I have to change the folder. There will be a warning, but there also will be some plots. So what those plots are and how to explain them, I first would like to go back and explain the concept of BRDF. The concept is very easy. In theory, if we have a surface, the surface reflects in all directions equally. If surface is doing that, for example, like calibration panel of ASD spectrometer, the surface is called Lambdortian. So it doesn't matter from which angle we look, we will always measure the same portion of reflected radius, so we will always compute the same reflectance. In a real life, however, it really depends on from which direction we look at, and we will see either higher or lower reflectance. In 2D view, in two-dimensional view, the concept seems very easy, but when it gets to three-dimensional, it becomes a bit more complicated. So in 3 dimensions, we still have solar light, which is at certain angle, solar zenith angle. We have sensor that views surface from certain viewing zenith angle, TTO in Scope. And we have the difference between them, which is a relative azimuth angle. So when simulating directional responses in SCOPE, we are going with a sensor to over all possible ranges of viewing zenith angles from 0 to 90, and to all possible relative azimuth angles from 0 to 360, in order to represent, and solar zenith angle stays constant as you provided it in the input, to simulate the response of the hemisphere. For a simple case, if we use the 3D views on that, we will see that, for example, if the surface is like a mirror, all incident light is reflected only in one direction. Then we will see BRDF like that. If it is 100% diffuse, Lambertian reflector to perfectly reflect in the hemisphere. However, the real surface is somewhere in between, so it's not a real mirror, it's not a real Lambertian, it's something like this. And here, two planes are important. One plane is where incident light and the normal to the surface are. This is called solar principal plane, so it's this one. And another one, orthogonal to that one, is cross principal plane. So I believe now we have all necessary information to look at the directional graph that was built with SCOPE. So here is how the graph looks like in 2D, here how it looks like in 3D, and here are the cross sections of this three-dimensional structure through principal plane, this one, and through cross principal plane, this one. So in any case, this point is an ideal direction when we look exactly from the top to the surface. In any case, we see that depending on the angle, we see either high reflectance, like on the edges, or we see lower reflectance, like in the center. This is well simulated here. An observation zenith angle from 90 is backscattering, so it's like from minus 90 to 0, and then from 0 to plus 90. That's what it means. But here we see the hotspot. The hotspot is exactly where around the solar zenith angle. It's very nicely seen on 3D. So if we align sun and sensor, we will be looking from behind, we will see no shadows. And that's why we see very high reflectance. Then it goes down, and minimal value is achieved somewhere here around 20 degrees as well. The cross principal plane, so this plane, also shows some effects of directionality, but roughly from minus 50 to plus 50 viewing zenith angles, the effect is not that strong. Yeah. So this is, once more, this is what we are seeing now on the graph below, cross principal plane, when we cross this figure. And this is what we see. If I was able to remove this line, we will see this peak is what we see on the principal plane. The same effects we can see through solar-induced fluorescence. For that, in the script, you will have to uncomment the following two lines. We run it. We see very similar, but the effect of hotspot is, of course, much lower. And the same we can see for thermal emitted radius. Here at, for example, 4,000 nanometers or 4 micrometers, the BRDF looks completely different. You see, the hotspot effect is very pronounced, but the other effects, it really looks like a hemisphere. This is the section that we see like that, across in the principal plane, and this is the effect over cross principal plane. If you want to simulate directional response, for example, for different solar zenith angle, then you can go to input folder and then input data default. You can set, for example, solar zenith angle, which is down here, TTS, to, let's say, more autumn solar zenith angle of 60 degrees. So we can save it, run it again. So if we plot the output now, for example, the same green output, we see that hotspot moved compared to the previous time. From 30 degrees, it moved towards 60 degrees. That's it. Now you know not only how to simulate bidirectional reflectance distribution function, but also bidirectional emittance distribution function for fluorescence and thermal radiance. See you in the next recordings.